really nice. But now, what am I talking about now here? Are there any functions that have reciprocals? I'm sorry. Sorry. I'm thinking of the trig. Are there any functions that have, what kind of functions have vertical asymptotes? Do you guys know? Well, they're really rational functions. What are rational functions from pre-calculus, I guess? R of x equals what? P of x over what? Q of x. What is P and Q? They are polynomials. I know I didn't give you the definition of polynomials. But where are the vertical asymptotes for any rational function? Do you guys know? Where the denominator equals 0. Rational functions are very, very what? Famous for their what? Vertical asymptotes. And they're easy to find. You just set the denominator equal to 0 and you solve for what? For x. Okay, so rational functions. Did you guys study rational functions in pre-calculus college algebra? The answer is what? Absolutely did. Okay, absolutely did. So there's something special about these here. Have you guys ever seen vertical asymptotes before? Say yes. The last few days. You see this function? Where does it have a vertical asymptote? Set the denominator equal to 0 and solve for x. Just by setting it equal to 0, you just found a vertical asymptote. Now that is a vertical line. So as you guys can see here, what do you know about that situation based on the last few days? I'm going to mention this to you guys. Let's put some of these ideas together. If I sketch this curve, what do you guys know I have to do? Did I pick up my pencil to sketch it? Yes. Yes, I did. Where did I pick it up at? At x is 0. Should I do it again? Did I do it too fast? Let me share with you guys this. I'm going to sketch this curve in green. Pick up my pencil. Now I have to continue to sketch it. Wherever I picked up my pencil, the function is not continuous there. It's not continuous at 0 because that's where the vertical asymptote is. I picked up my pencil. So this is continuous everywhere else, but at 0, you got a problem here. So what happens, generally speaking, in a Calculus 1 course is when they give you a rational function like this, they love to give you what? Limit questions at those locations. Now, you already know what this answer is. That does not exist because we looked at the numerical approach to these.
Yeah, they are not equal.
What do I mean? What's the limit as x goes to 0 from the left? And what's the limit as x goes to 0 from the what? From the right, ladies and gentlemen. What are those two limits? Negative infinity for the left-handed limit and what? Positive infinity for the right-handed limit. So we've been looking at this picture, but what you don't realize, is you're really looking at the location where that function is not continuous. You cannot apply the direct substitution principle here. You know what's going to happen? What are you going to do? Let's say you forget. You go, okay, Mr. Judge, I'm going to do direct sub, right? You go, I'm stubborn. That's okay. That's all right. But what is 1 over 0? Well, if you plug it in your calculator, and that's a programmer, I would lecture the programmer. I'd say, programmer, don't put error. Say undefined. 1 over 0 is what? Undefined. So I want you guys to remember, is undefined the same as not existing? No, they're not the same things. Does not exist applies to the left-handed limit not equal to the right-handed limit. Being undefined is functional evaluation, and 1 over 0 is just not defined. There's no definition of that. So I want to say to you guys, you can't use continuity or direct sub. In fact, the function is discontinuous where? At what? At x equals 0. So that curve has a what? Vertical asymptote at 0. And so what I did with this worksheet is, and by the way, though, I got news for you guys. I know I'm out of time, but I'm just too excited. What about at 1? Can I use direct substitution when x is now at 1? Is the function continuous at 1? It sure is. How do you know? Can I draw that portion around 1 without picking up my pencil? Yes. And I'm using the wrong colors. But my point to you guys is this. Okay, the left-handed limit equals the right-handed limit around 1, but it's not happening around what? 0. It's a different question. So here, we can say 1 over 1, which is what? Which is what number? 1. So you could use direct substitution for a rational function with a vertical asymptote. You just can't use it at the vertical asymptote. You could use it everywhere else, though. So you can do this all day long. You say, what about round 2? What's the limit? 1/2. What about around 3? What's the limit? 1/3. What about around -2? What's the limit? -1/2. What about -10? -1/10. You can do it. You can use direct sub all day long. You just cannot do it around the what? Vertical asymptotes. Isn't that pretty nice? What do you guys think? So, I mean, we're out of time. I could keep going, but we're out of time. And, as you guys can see, I had a lot more to talk about. Where's our vertical asymptote here? Do you have a rational function? Say yes. How do you find vertical asymptotes? Let x squared equal to 0, solve for x. What does that mean? X is 0 is your vertical asymptote. You could have said, I can see that by the graph. So what do you guys know about the graph around 0? What's your limit around 0 here? Oh, let's take a look. Let's see if you guys are awake. Limit x is 0, 1 over what? X squared. What is this? That's infinity. Why can I say infinity? They both go to the same what? Direction, same place, heaven. How is that different from this one? One's going to heaven, one's going where? Yes, okay. Sorry. One's going down forever, and one's going up forever around 0, right? And in this case here, you know, they're both going what? Up. And what I'm saying is, as x goes to 0 from the left, it's infinity. And as you go to 0 from the what? From the right, it's also infinity. That's what I'm saying. And so we're kind of where we've been talking about, if you guys want to know what I'm saying. Now, I'll continue with this discussion in the future, but what I'm getting at is all the nice permutations about vertical asymptotes. When do you say does not exist? When do you say is infinity? When do you say is negative infinity, right? You guys get the picture? All right, remember, did I put some homework in? 1 over x squared. Okay, so I see where we're at. And what I want to remark, though, is what I did. There you go. You're going to see this sheet now. So I did update the sheet for you. So you say, you updated that? Yeah. I actually, you know, put some, I don't know. It's not so generic, I should say. And so I did update that for you guys. So you might want to download that and take a look at it. It was updated. We were on vertical asymptotes, right? So I think we're going to, so there we go. There's this situation we talked about. So, you know, this is going to be, for example, I'll put some more, I'll probably update this when I get home as well. We talked about those kind of situations. And I'll update that too. I think I didn't get a chance to finish that update, but whatever. We looked at that. I actually put the vertical asymptotes there. And this is what I wanted to talk about here. Okay, so I did a little bit of updating of that worksheet. Now, here's an example here I want to talk about. When you're dealing with limits for this vertical asymptote, again, they're going to want you guys to understand and know, where do you have the vertical asymptote? Right? In your notes, where do we see? Where do you have vertical asymptotes for rational functions? What's that? That means x minus 3 equals what? 0. It's where your denominator equals 0. Is that right? When you have a rational function. So what does that mean about the value of x if you solve for x? Yeah, that means x equals 3. It means you have a vertical asymptote at that location. Okay, you guys okay with that? All right, now, the graph, what you guys see here, is exactly that in the graph. So this is where that x is 3 would be. So what kind of questions do you think they're going to want to ask you if I said to you guys, right? You know what they're going to ask? You're going to say, what's the limit as x goes to 3 from the left of 1 over x minus 3? Okay, they're going to want to know, what's the limit as x goes to 3 now from the right of 1 over what? X minus 3. So around 3 from the left, what do you think your limit's going to be? This is the graph. Why do you think that's negative infinity if you approach 3 from the left? Yeah, all those, yeah, it's the y coordinate value. You guys remember that? That's going down what? Forever. So that limit's going to be what? Negative infinity. Is that right? And then to the right of 3, what's going on here? The opposite is happening. All those ordered pairs, the y value is going up forever. So what does that mean? That's positive infinity. All right, you guys okay with that? Now, what's the limit then? What does this mean here for us, for the limit as x goes to 3 in general of this curve? Why do you say does not exist? They're not the same. Is that right? So, oh, sorry, that's not a highlighter. So these two are not the same. So that's why you say does not exist. So I wanted to kind of update a little bit of this and give you a little bit of some, I would say, somewhat variation. But, you know, this is what they're asking around a vertical asymptote, okay? Now, I want you guys to also note something you want to know about this, because this is something that calculus students get wrong when they first learn it. If I can find my eraser. Let's see if you guys are awake about this here, okay? If they ask you now, what's the value of the function, what's f of 3? What is this going to be? Okay. They want to know functional evaluation at 3 now. They're not talking about your approach, your left-handed approach, or your right-handed approach. What's the value of the function at 3? If you plug it in, let's say you plug it in. You get 1 over what? 3 minus 3, which is 1 over 0. And you guys can't see that. What does that mean to have 1 over 0? Your function's undefined. Is that the same as does not exist? No, that's not the same. So I want you guys to understand. That's undefined. Okay? All right, you guys okay with that? Easy peasy lemon squeezy? So there's the difference between the approach, and then there's a difference between what? At the location. Now you might say, what are you getting at here? Let me remind you guys here. Let's ask you this kind of question. Since we're doing, I give you guys that definition too, right? Remember, if the limit of x approaches 3 of this function equals f of 3, then we can say that this is the function's continuous at 3. Is that right? But what do you guys know? Those two things are not equal. You go, what are you talking about? Well, you know the limit, the left one, this does not exist. So this answer is the limit question. Okay? This does not exist. This is the argument for it. This answer here, f of 3, what do we say? This one was undefined. And we know that those two things are not the same things. Does not exist is not the same as being undefined. Therefore, what's your conclusion about continuity at 3? Yeah, f is discontinuous at x equals 3. So I'm just pointing out to you what your book and the homework's going to want to always do. They're going to check to see, do you understand these ideas? And if I said to you, you know how you draw the curve again, like we looked at? You sketch this curve. Didn't you pick up your pencil at 3 to continue? The answer is yes. So it's discontinuous at 3. Remember, that's the idea. So, ladies and gentlemen, these are some very important details. Putting together limits and the value of the function at the location, they're two different things. Approach is a limit, and then the value at a function is something different. And they always like to test you around the what? Vertical asymptotes. All right, you guys okay with that? So that's why I rewrote some of this, and I did what? I gave you guys a little bit more of what? Variety. You go, variety? What about this question here? Do you have any vertical asymptotes here? Well, you have the graph there. Where do you have a vertical asymptote? Remember, this is from pre-calculus or college algebra. Vertical asymptotes happen where the denominator equals what? So solve for x, set that equal to 0, solve for x, and what do you get? And this is your vertical asymptote. Is that right? So functions are not continuous at vertical asymptotes, ladies and gentlemen. Okay? They're not continuous there. So at x is -2, you're going to see that here. You go, oh, is that where -2 is? It sure is. So the limit let's see if you guys can tell me. What's the left-handed limit? Where are your points going to? Yeah, the y-coordinate's going to positive infinity. So you can say the limit as x goes to -2 from the left of the curve -1 over x plus 2. Okay? That equals what? What is that? Where's that going? Positive infinity. Good. Let's change the color. Limit x goes to -2 from the right of negative what? 1 over x plus 2. Where are you going now? That's negative infinity. Is that right? All right. Then what does that mean, generally speaking? Limit as x goes to -2 of -1 over x plus 2 now does not exist. And you might say, Mr. Judge, why is that answer does not exist? Because both the left-handed limit and the right-handed limit are not the same answers. Okay, they're going to different places. So that's, again, a picture of around a vertical asymptote, again, of a limit where it does not exist. And then now, again, you guys know what's the other question they may ask? Well, they want you, maybe, do you understand what does it mean to evaluate the function at that location, x -2? So if you said, oh, I'm going to plug in a -2 here, and what do you get? What do you end up getting? Yeah, you get -1 over 0, which is undefined. And again, we can conclude that f is discontinuous, not continuous, at x equals -2, simply because it does not satisfy the definition, where the limit equals the value of the what? Of the function. Now, here's what's going to happen. You might say, okay, Mr. Judge, that's amazing. That's great when I have a graph, but, what if I know nothing about curves? What if, Mr. Judge, I went straight from beginning algebra to calculus 1. I've never seen that, right? You go, okay, well, it's not a good sign, but nevertheless, what does this say? Curves every B-STEM student should know. So there's all of these graphing, techniques that you learn in like pre-calculus, college algebra, intermediate algebra. The reason they graph, ladies and gentlemen, is because they use these things. Notice the family 1 over x. It's on the left there, right? And if, and that's the family of curves. That's the whole idea. But that's not f equals -1 over x. What does the negative sign do to any curve? Reflects it about the x-axis. So, but you start, this is your reference. That's how this works historically. People have had what? These curves, right? 1 over x squared, a family of curves. 10 to the x, e to the x. These are all families of curves that you guys want to be aware of. But, what started to happen at some point is that they started to integrate like numerical. They started looking at this numerically in a lot more detail. And so what if you said, how do I handle this numerically? You're approaching what number? Let's say you said to me, what if I use the TI, and I can even go back to this original question, x 1 over x minus 3, and we're looking at limits around 3. All right? How would you approach this from the left? Right? Yeah, you're going to have to know what's to the left of 3. you might start to use x being what? 2.9. And I think your book will say try x is 2.9. Do you guys know that? If you look at the book, x is 2.9, 2.99, and what else? 2.999 type of thing. You're going to plug that in where? Down here for x. Those are all numbers to the left, and they're getting closer. So the book even tells you, hey, use your calculator, but you're going to say 1 divided now, plug in 2.9 now for x, minus 3, close that up, and what do you end up with? You say, I get this number, negative 10. Okay. But get closer now. 1 divided by what? 2.99 minus 3. Close that. What do you end up with? Negative 100. Okay. Now get even what? Closer. 1 divided by 2 point what? 999. That's pretty close to 3 from the left. Close that. And what do you end up with? Negative 1,000. Now you might say, can I continue? If you like. How do I get closer? Add another 9. Add 4 nines now. Minus the 3. Close that. And ladies and gentlemen, there it is. Now, what are you actually looking at? You're looking at a what? A pattern. Is that true? What's the pattern? Well, let's be careful. First of all, the number's negative. Negative 10, negative 100, negative 1,000, negative 10,000. What do you think? If you get even closer to 3 from the left, what might you get? Negative 100,000. If you don't believe me, try it out. So what if you said to me on a test, they asked you this question, and for the left-handed limit, you say, you do this. Negative 100,000. All right. I'm going to mark it what? Wrong. Why? First of all, it's not the answer.
It's not definite.
Hmm?
This limit is not definite. It's indefinite.
No. Well, first of all, a couple of things. That's infinite. This is finite. You're telling me the answer is finite when it's actually an infinite answer. So what you're also telling me is you don't know about what approaching means. In other words, you're saying you don't know what a limit is. A limit is a what? An approach. It's not the value out of function, even though you're doing functional evaluation. And you go, what? But I'm doing functional evaluation. Yeah, but in theory, you have to continue getting closer to that 3 from the left forever. Now, you really can't do that because you'll die. Because forever is a long time. So you can't say, I'm going to put 2 with 500,000 nines next to it, minus 3, and you still don't know the answer. So at that point, you're not looking at the pattern, you know what I mean? And so really, you say, well, how do I learn this? By studying what we're doing. You do it numerically and you do it graphically. You put the idea of a limit together that way. And that's the left-handed limit. So that's your conclusion. Your book has questions like that. And then you say, well, what about you have to approach from the right now? Well, what numbers are to the right of 3?
3.
You can say 3.1, and then you can say, let me get closer to, 3.1 is pretty close to 3. Was that true? How do you get even closer? 3.01, and then what else? 3.001. You just keep adding those what? Those zeros now, and that's pretty close to 1. And then you say, well, what do I get here? And that's how you handle that. I'm going to clear this out. I'm going to say 1 divided by 3.1 minus 3, and I close that. What do you end up with? 10. Is that the answer? No. 1 divided by what? 3.01 minus 3. Close that. And what do you get? 100. Is that the answer? No. 1 divided by 3 point what? 001 minus 3. There you go. Okay. What are you really looking for? Is that the answer? No. 1 divided by 3 point. Okay, you go, Mr. Judge, I'm going to put a lot of zeros in a 1. I'm going to get even closer. I'm so excited. Oops. Don't forget to put minus what? 3. Close that. Is that, and then you say, it gave me, what did it give you? What is that? Scientific what? Notation. You guys know what that is? That's 1 times 10 with 10 to the 12th power. That's really 1 with 12 zeros. That's a pretty big number. Is that right? It's still finite, but you're supposed to be looking at the approach. You're looking at the pattern. So what's happening with this pattern? 10, 100,000, 10,000, 100,000, million, billion, trillion, blah, blah, blah. This is going where? To infinity. So ladies and gentlemen, that's what you're looking for is the pattern. And then there's your answer. Your answer is what? Infinity here. You guys okay with that? Because you see it better. So that's kind of what's going on here, ladies and gentlemen. You're seeking to see the pattern numerically in your calculator. So there's some questions in your book that way that say, hey, try to see what this is by plugging in these values in your calculator. And there you go. But you're looking at this how? Graphically and numerically. Approach, and then the value at the location. You could do the same thing here, okay? What about this situation? I think, well, we actually did that example. We did that. That's in your notes. So we're looking at this at vertical asymptotes. What if you said, Mr. Judge, what about this one? Okay. All right. First of all, I want to remind you guys, what family of curves is this in? This is in the family. Yeah. So in my mind, 1 over x squared. And what I remember about this curve personally, I write that stuff down. It looks like this. Is that right? And then what if you put the negative sign? Oh, it looks now like what? Like that. So these limits are both going to the same location. You with me on this? All right. But now, it's a rational. It's a denominator. What do I do with that denominator? Has vertical asymptote. You set x minus 4 squared equal to 0, and then you solve for x. So do you guys remember how to do that? How do you do that, right? What does that mean? That means x minus 4 equals 0, and then that means x equals 4 by adding 4 to both sides. This is the location of your what? And sure enough, in the graph, what do you guys see? And doesn't it open down like that forever? Do you see what I'm saying? So this is how you, in my mind, I think of it. Oh, family of curves, 1 over x squared. It looks like a volcano. And then with the negative sign, it's inverted. And then what do? I know what this picture is. Left-handed limit. I'm going where? Where are you going? Down forever. So that's going to be what? Okay, the right-handed limit. What am I doing? Down forever. So when they ask you, hey, what's the limit? X goes to 4 from the left of negative 1 over x minus 4 squared, the function, well, that's positive infinity. Okay? And the other one, they say, oh, what's the limit again? X goes to what? 4 from the right of negative what? 1 over x minus 4 squared again. What's this? Positive infinity. What's your answer? Limit x goes to 4 in general of negative 1 over x minus 4 squared. What's this going to be if it goes to the, oops, I think this is negative, right?
It's negative, yeah.
It's negative. Negative. It's going to the same what?
Direction.
It's going in the same direction. What does that mean? This is equal to what? Negative infinity. So this is a negative infinity answer. All right, you guys okay with that? And you're looking at the direction. This is the limit. This is an approach. This is not the value of the function. So what if they said, hey, can you tell me what's the value of this function at 4? Well, what do you guys know? What's always the case for the values of functions at the vertical asymptote? Undefined. So one is an approach. The other is what? At the location. At the location and what? Approach. Let's see if you're really awake. Oops. I want the highlighter. What does this piece of information tell you? F is what? Discontinuous, not continuous. At what location? At x equals 4. Right? Remember that? Because if you draw your curve, you sketch this, at x equals 4, I picked up my pencil, and then I have to continue, and there it is. So again, they like to test you on limits at vertical asymptotes. They want to see, do you know what's happening with your curve at the vertical asymptote? They love doing that. Common thing to do. Anybody have any questions on that one? No? What about this one here? You go, oh, this is minus 2x cubed. What family does that belong to? That's 1 over x cubed. Now, 1 over x cubed looks like this, ladies and gentlemen. And then the second you put any negative sign, oh, reflected about the what? X-axis. Oops, I think I have it backwards. Sorry. I have it backwards. Let me actually think and wake up. Yeah, looks like this. And then put the negative sign reflected about the what? The x-axis. Do you guys remember that from pre-calculus? Those kind of things, you guys remember? All right, so then you go, oh, that's the curve. So it doesn't matter if it's a -2, it just makes it the shape a little bit different, you know, that constant in front. But here's the thing, at the vertical asymptote, you go, I don't know where that is. Well, you set what? You set x cubed, the denominator equal to 0. You solve for x, what does that give you? Okay. So what do you think now? And there is where your x is 0. What's the limit, the left-handed limit going to be of this function? Positive infinity. You're approaching around 0. Where are you going? Up forever. Is that right? And this is really the y-coordinate value. So to the left, around 0, it's going up. To the right, around 0, it's going how? Down. Limit x goes to 0 from the left of the negative what? 2 over x cubed. What does that equal? Positive infinity. And then what about from the right? Yep, it's going to be negative infinity. So what do you think that means here? Limit x goes to what? 0 in general. What do we say if it's going to different locations? Does not exist. And then could you do this in your calculator?
Yeah.
Yes, numerically, you know. So, I mean, this is kind of the details, ladies and gentlemen, that, you know, and I went back to rewrite because I wanted to include some shifting on people because your book has some shifting. All right. You might say, oh, Mr. Judge, what is this? Well, that's kind of just like what you already did. But your vertical asymptote now, where's that going to be? Where x plus 2 to the third power equals 0. Is that right? And that implies x plus 2 is 0, which really means x will be negative 2, and that's the location of your vertical asymptote. So double check. Is that happening? Yes, it's right here. All right, you guys okay with that? So let's look at the logic here, because logically speaking, there's that third power again. So it's in the family of curves. Curves, every B STEM student should know. 1 over x cubed. How does that curve look? It looks like 1 over x. So that's in the same family. 1 over x to the odd powers. You guys with me on that? Oh, and then I see a typo. Oh my God. That's a typo. How do you guys notice? What should I do? Let's do this. Power 2. Oh my God. Never ending. I don't know. You know what it is? I when you multitask and do all that, it just kind of, whatever, horrible. Elon Musk is not going to buy this. Now I have to go notice how to fix this up. That's okay. We want a volcano question. But this is around 0. Is that true? That's the family of curves around 0. This was shifted to the left 2 units because that's a left shift. When you have the x plus something, right? X plus a or x plus 2, that was shifted to the left 2 units. So it's the volcano shifted to the left 2 units, really. All right. That's essentially how you graph in pre-calculus and even in what other course? College algebra. It's a shifting graphing course. All right, but what's the limit questions? Around -2. So to the left, what's happening with these, the y coordinate, these points? Aren't you going up forever? What's happening to the right? Same exact thing, going up forever. So the left-handed limit is the same as the right-handed limit. And what's that curve? 4 over what? X plus 2 squared is, what is it? Where's it going? Positive infinity. Okay. And then, and that was to the what? To the left. And then limit. X goes to -2 from the right. Positive infinity. Is that right? They're both going up. Limit. X goes to -2 in general. What do we say now? Isn't that the same location? All right, there you go. It's going in the same direction. Left and right. That's all you're saying. So you're putting Math 260 together with calculus. And then seeing if you're awake, what's the value of the function at -2? Undefined. What always happens for functions at vertical asymptotes? F is what? It's undefined, but it's also discontinuous. That always happens at your what? Vertical asymptotes.
Because they're not equal.
Yeah, essentially by definition, infinity is not the same as undefined. You think it is, but it's not. It's really by definition. Right here. This is two different things. But also, there's no way you can draw that curve without picking up your pencil at what? -2. And I want you guys to do this. I'm going to do this to you guys here because this is something that, math instructors love doing, especially myself. They might even ask you, what's the limit as x goes to 0 for 4 over what? X plus 2 squared. Okay. And you might say, but Mr. Judge, that's not at a vertical asymptote. And I'll say, I know. But take a look at what's happening here around 0. What's happening around, what's that point, by the way? Isn't that 0 what? Do you guys know what that location is? That's 0, 2. Is that right? So if I sketch my curve for this portion of the curve, you see at that point, did I pick up my pencil? No. What do you think that means? It's continuous. At what? At what value for x? Remember, this is the x value, and the limit is the y value. Oh, it might be 1, sorry. Is it 1? Ah, then it's a different curve, sorry. But don't worry. I have to fix it anyway. Don't see that. Don't see that. That's not even there. I think what I put it, I think I might have left the wrong curve is what I did in Desmos. Okay? And so how do I know it's going to be a 2? Does anybody know what I'm getting at? How do I know it's 2? What happens because of that, if I plug in 0 for x, oh, it's not even 2. You're right, it is 1. Sorry. You're right. It is the right curve. It is 1. Okay. You're right. Okay, that's 1. How do I know this? If you plug in the value, remember we're plugging in the value? What does that equal? 2 squared is 4. And what does that equal? 1. What did I just do? Anybody know what I just did? Yeah, your book calls this what? At this point, they say use what? Direct what? Substitution. All that means is directly substitute the value of x into the function, and you get that finite number of 1. The reason you do is because why? This was what I was getting at. Sketch the curve. The reason you get that answer is because your function f is what? Continuous. Where? At x equals 0. Yes. So the right-handed limit, graphically speaking, equals the left-handed limit. You're both approaching what? 1 as a y value from both directions, from the left and from the right, and more importantly, it equals the value of the function. And that's it. Your approach is the same as the value of the function. That's called being continuous at the point. And so a lot of times instructors do like to check, even though they gave you a vertical asymptote setting, you're focused on the vertical asymptote and the behavior, but then they might want to plug in another value and say, what's the limit? And it's gonna be continuous at that point. And It's called direct sub. So it's, I like to approach the limit questions the way I do it this way. I think it makes it easier to understand. Your book doesn't approach it exactly the way I do it. But if you guys notice, I'm not focusing on the book yet. And that's the reason. Anyway, you could do this all day long. Here's what I want to get at. Yeah, I mean, we could do the trig functions too. But, you guys can look at the vertical asymptotes there. Here's what I want to get at. Same thing has vertical asymptotes. Let's try something like this. You say, what do you mean? Do you guys remember these functions? What's interesting about these functions? They're still rational functions. What's happening now with your vertical asymptotes? There's two. You say, how do I know? Because you have to always set the denominator equal to 0. And then you solve for x. So how do you solve this for x? What do we use from beginning algebra, right? X equals 0. X minus 3 is 0. That's called the zero product rule. If you guys remember the zero product rule. So you now get x equals what number? 3. So x is 0 and x is what? 3. You have two vertical asymptotes now. Oh, here and where? Here at x is 3 and x is 0. So what do you think they're going to want to ask you? See if you guys are awake. What's the limit as x approaches 0 of 1 over x times x minus 3 here? So around 0, what's the limit? You guys can see it in the picture by now. What do you guys see? Be careful. Does not exist. Is that true? Because both sides around 0 are going in opposite directions. Okay. What about around 3? Same thing. Outstanding. Limit as x goes to what? 0. I'm sorry. We changed that 3. 1 over x, x minus 3. That's also a what? D&E. What if you said, Mr. Judge, how would I do that in my calculator? Well, get close to 0 from both sides. Get close to 3 from both sides. See the what? The pattern. So your book wants you to do that. And of course, the values of the function at those locations are undefined. And of course, you guys know they're discontinuous at those values. But how about this? So what if they said, what's the limit as x goes to 1 over what? 1 over x, x minus 3. What do you guys know about this? See if you guys can put these ideas together. What's this limit going to be? What do you know? This curve is continuous everywhere but at 0 or 3. Is that right? Your vertical asymptotes. What does that mean you're free to do? Yeah, direct sub. You plug it in because remember, you sketch this curve. Sketch the curve. All the other locations to sketch, we didn't have to pick up our pencil. So you are free to use direct substitution, plug in 1, wherever there's an x. 1 over 1 times 1 minus 3. What's that? 1 over 1 times negative 2, which is negative what? 1/2. So you could use direct substitution. Your book will say that, or it's really continuity. That's really because the function's continuous at 1. So that's the justification. F is what? Continuous at x equals 1. So you're just plugging that number in. You got a finite answer. Do you guys see? Is that easy peasy lemon squeezy? Which kind of functions are really nice? We talked about them last week. Which ones are the nicest functions you could take limits for? Polynomials. Why? Continuous everywhere. And then sine and cosine, continuous everywhere. We might have to go back and do some trig functions. But I'm having too much fun doing some of these. You guys think you can answer this question?
Yeah.
You guys think you can answer these here, x squared and x plus 5? Where are the vertical asymptotes? You said x squared and x plus 5 equal to 0. What does that mean? X squared is 0. It means x is 0. What about x plus 5? X is negative 5. Okay. So at x is 0, and x is what? Negative 5. That's where negative 5 is. We have vertical what? Asymptotes. So the function's not continuous at those points. Okay, it's not defined at those points. Everywhere else it is. So they're going to want to say, okay, can you tell me what's the limit as x goes to negative 5 of that function 1 over x squared x plus 5? What are you guys going to say just looking at the curve? What are you going to say? You're going to say what? Does not exist. What's the limit as x goes to 0 of that function? 1 over x squared x plus 5. What's this limit going to be? Positive infinity. Good. It's that volcano. Is that right? Goes up forever. All right. And then, what's the limit as x goes to 2 for 1 over x squared x plus 5? What's that limit at 2? What do you guys know that you can do at 2? Just plug it in. Because it's continuous at that location. 1 over 2 squared. 2 plus 5. Is that right? Didn't you just plug in the 2? So that's 1 over 4 times 7. You guys know that's 1 over what? 28. You got the value of the function here. Easy peasy lemon what? Squeezy. You go, I don't know. Well, it's way over here. You know, that point, x is 2, y is that decimal, that location. And you can get away with plugging it in because the function's continuous at that point. That's all. Okay. All right. Now, this is an interesting question because it's still rational. But where do you have that vertical asymptote? Right? Where do you have this vertical asymptote? The vertical asymptote is going to be where 2x plus 5 equals 0. If you solve for x, you guys know what you get? It's negative 5 halves, or negative 2.5. So this is where your vertical asymptote is. This is the location where you cannot plug anything in, right? If the value of the function at negative 5 halves, which is negative 2.5, is undefined. So what do you think they're going to ask you? They're going to say, what's the what? Limit at that location. They're going to say, what's the limit? X goes to negative 5 halves for, 3x plus 1 over the 2x plus 5. How does that curve behave? To the left, it goes up forever. That's infinity. The left-handed limit is infinity. What's the right-handed limit? Negative infinity. What does that equal?
Does not exist.
All right. And of course, you might say f of negative 5 halves equals what is undefined. And then what you can really say, if they asked you, they'll say, okay, what's the limit is at any other point? Right? You know this function's continuous how? Everywhere else except at 5 halves. So we can just do what? Plug in 0. So say, is that, let's use 3 times 0 for x plus 1 over what? 2 times 0 plus 5 by direct what? Sub. And that's just 1 what? 5th. Bless you. Easy peasy lemon squeezy. And you say, well, what's going on around that x is 0 right here is what they're talking about. That point. X is 0, y is 1/5, I guess. So the behavior to the left of it and the right of it, they go to the same location and they go to the value of the function.